Today's memes, again, I'm starting to make my own. Okay, you might have heard this one, but I don't know if you know the original. Like the original is if you're not a part of the solution, you're part of the problem. It's kind of a motivational thing telling you to shape up. And so chemists like to come in and say, if you're not a part of the solution, you are the precipitate. So today we're talking about precipitation reactions. So I was like, hey, we got to make a meme precipitation. And then we're going to talk about acids today, acids and bases. And so to introduce acids, there's different ways to describe what an acid is. And so you could say, in fact, we've already done that because we had to name acids. And so how do I get you to name acids and recognize acids without you knowing what the true definition of an acid was? And so I taught you the very simplest way to make an acid. You take an anion like sulfate that has a 2- on it, and you add 2 protons. So that's the top poo here. Acids are just protons added to anions. And so that's where you are. But a little more sophisticated definition would acids produce protons in water. So when they go into water, they produce hydrogen ions in water. Hydrogen ion is a proton, okay? But then the more sophisticated answer is that acids donate protons. And that's a generic definition of an acid. So if a substance donates a proton, it may not be an anion with protons added to it. It could be something else, but like a weak acid. And today we're going to talk about strong and weak acids. And so that's the better definition of an acid. Is an acid is a proton donor, and then a base would be a proton acceptor. So we're going to learn about that today too. So here's the progress on tonight's homework, and I've got a concern. Okay, there's some people that are jumping on it, and looking back at the exam and the sort of the breakdown of the grades at this point in the course. Here's the A, B, C, D, F breakdown. And I noticed that these numbers are very similar. So that adds up to about 40. And there's about 40 people not jumping on the homework every day to kind of get something done each day. And so it's maybe not a coincidence, okay? So take a little bit every day. You should have at least, a couple of topics a day that you're working on so that you're not holding everything off to the day it's due and running into trouble. Okay, here's the things that we're covering today. It looks like a lot, but a lot of these are just, recognizing and selecting check marks. There's not a lot of calculations in this homework set. So we want to think about how things dissolve in water, and not everything produces cations and anions when they go into water. Most notably, organic molecules pretty much stay as a molecule in water. They don't break off and make ions, okay? Organic acids might be weak acids. They might produce a small amount of ions in water. So there'd be an anion and a cation, but it might be like for 100%, like if you put this molecule in there, only 0.00001% would ionize and make protons in an anion. So it says in the problem, each one of these is soluble in water. Later on today, there's going to be several that are not soluble in water. So we're going to learn about solubility rules today too. So acetone, when it goes into water, it's an organic molecule, so there's no change on dissolution. So it just goes right into water. So the major species present when dissolved in water, of course, would be water. So every one of these is going to have water. And then whatever the molecule will be, or if it breaks into ions, then it would be the ions. So it's just trying to get you to think about when the substance goes into water, what happens? Well, the thing that bothers me about this set of homework on Alex is it's much easier to just show AQ on the end of this thing. So I don't know why they didn't include AQ here. So, aqueous for this molecule, you could just say that molecular formula and put AQ behind it, and AQ is aqueous. That means it's dissolved in water. Okay. Same for propylene glycol. It's an organic molecule, so no change when it dissolves. Then you would have this propylene glycol AQ and H2O, but Alex just wants the molecules. It doesn't want the H2O liquid or the AQ designation. What about iron 2 chloride? Okay, it says up there that all these compounds are soluble in water. So this is an ionic substance. When ionic substances go into water, if they're soluble, they break into their ions. So water actually tears this substance apart. So if we have an iron chloride crystal, drop it into water, then the water is going to tear it apart. Why? Well, because water has kind of a positive end and a negative end. If you look at water, this is the molecular shape of water. And you have these lone pairs up here. We'll get to Lewis dot structures later. But this end of the molecule is negative, and this end of the molecule is positive. Because of those hydrogens, those protons, all the electrons are pulled towards the nucleus of oxygen, because oxygen has 6 protons and hydrogens only have 1. So 6 protons pull all the electrons towards the oxygen. And it'll actually have all 8 of them, so it can look like neon. So oxygen really wants to have 8 electrons around it, so it'll pull those electrons towards it to try to get that neon cloud, that stable electron cloud, and that exposes those hydrogens and makes them very positive. So we have a very positive end of water and a very negative end of water. So we've got an iron chloride crystal in here. The positives go over there and grab those chlorides. And so you can get 6 water molecules around a chloride to stabilize it in water. And so you'll have a chloride ion and 6 water molecules around it where their hydrogens are all pointed at the chloride. And so then that helps that chloride stay in solution. Once it gets into solution, it's going to have a hard time finding an iron cation to precipitate with, because the water is surrounding the chloride. So it becomes a cage around the chloride ion. So it's sort of single direction. Once it dissolves, it's hard to get back to a solid state. Same with the iron, only it's the oxygens going around the iron. So you have an iron cation, and then the oxygens are pointed towards the iron, and the hydrogens are farther away from the iron cation. And that stabilizes the iron ion in solution. And so this dissolves. So in solution, it's an ionic compound, so it makes ions in aqueous solution. So we have water, iron cations, and chloride anions. Yes?
So would that be like gasoline in water? Like you can see the gasoline physically with your naked eye. Would you be able to do that with the organic compounds, or is that?
Okay, so what you're seeing when you have gasoline with water is gasoline, that molecule is long enough and doesn't have any oxygens on it. So it's not even dissolving in the water. It's floating on top. So what you're seeing is a really thin layer of gasoline. And you're not seeing the color of gasoline. What you're seeing is light bouncing in that thin layer and giving you kind of a rainbow effect. Yeah, so when you get to PChem 1, 4448, we start talking about diffraction and the way light interacts with thin layers of things. And so that's what you're seeing is diffraction pattern and refraction because of the gasoline, that thin layer. So you get that rainbow effect from the gasoline on the top. If you were to put enough oxygens on that molecule, then it would be soluble in water. So if you notice, these organic molecules have OHs and what we call a carbonyl, so oxygen on there, which makes it more like water. So like dissolves like. If it becomes more like water, it'll be soluble in water. Whereas gasoline itself is like hexane. So hexane and heptane, all these long chain molecules with no oxygens. So they just separate. It's like a real thin oil. So oil and water don't mix. You may have heard that. It's because they're so dissimilar. So let's talk about these types of equations that we're going to be looking at next on Alex. So if we have substances, when they dissolve in water, they become aqueous, okay? And if it's a soluble ionic substance, it breaks into ions that are aqueous. So sodium chloride, we put that in water. We could write its molecular formula and put aqueous behind it. But what's really happening is that there's sodium ions that are aqueous and chloride ions that are aqueous. Insoluble ionic substances don't break into ions, but will stay solid. So we would indicate this like silver chloride. We put a solid behind that, and you put it into water, it stays solid. So you have a solid silver chloride, you scrape it out of the bottle and stick it in water, it's just going to sit on the bottom and just not do anything. So we have silver chloride, and we would show that it's not doing anything by just having solid behind it. Okay. Soluble molecular and organic substances will not break up, but will stay aqueous. So in this case, we have methanol. We could have methanol liquid. We could add it to water, and it would just become methanol aqueous as it dissolves in water. Okay. But notice there's lots of different ways to write these substances. You can indicate with solid, aqueous, and so on. So we have these different equations that we'll talk about. One is the molecular equation. So that's when we keep the molecule formulas together. They can still be aqueous, but we just don't break them apart. And so in this case, when we talk about keeping the molecular formulas together, this is what I'm talking about. It's dissolved in water, it's aqueous, but we're just keeping that molecular NaCl together, okay, in the formula. Okay, ionic equations, they split all of the soluble ionic subspecies apart. So these guys right here, when we say split it apart, that's what we're doing right here. And then the net ionic equations, they cancel what we call spectator ions. And so we're going to do a couple of problems, and I want to introduce that vocabulary word or that term spectator ion as we do one of the problems, okay? Because that's an important concept, and we can't get to the net ionic equation without understanding that spectator ions on both sides of the arrows can just be ignored because they're not participating in the reaction at all. So this one, it says write the net ionic equation for this right here. So the following chemical reaction takes place in aqueous solution. Write the net ionic equation for this reaction. So look at that equation. That is the molecular equation. So this molecular equation, notice that this says aqueous, and yet it's written as if it's a molecule that's still together. Okay, so all of these aqueous species are written with their cations and anions next to each other as if it's a single species, and yet it's aqueous. So when it's aqueous, if it's soluble, this means it's going to be broken apart. So then, so we first write the full ionic equation before canceling the spectator ions. So this is a really long equation, so it may be hard to see in the back, but let me just walk you through what we have. So we've taken this iron chloride and we've broken it into two irons. See, there's two in front, so two iron cations. Okay, that should actually be a 3+. So let me just correct that mistake real quick. So this should be a 3+. Okay. And then we have 2 times 3 for the chlorides, and so we have 6 chloride ions. Okay, so when they break apart, then you get 6 of those chloride ions. Then we have here this ammonium ion. It's ammonium cation, and when it's bonded to sulfur, you need 2 of those because this is a +1. A sulfide is 2-. So we have 2 of those to neutralize the 2- on the sulfide. And then this whole molecule, when we balance the equation, we need 3 of them. So 3 times 2 is 6 ammonium ions, aqueous. And then 3 times the S, so S2-. There's 3 of those. So you see we've taken everything in the molecular equation and broken it into the ions that are soluble in water. Pretty straightforward. Any questions about that before we go to the right side of the equation?
So we get on the sulfur, the 2- just comes from sulfur being.
Yeah, so exactly. So we're right over here. Yeah. So we're right here in group 7A. No, 6A. So we're 2 away from 8. So this is O2- and S2-. Okay. And so then let's work on the right side of the equation. Look at up here at the molecular equation. We see this is a precipitation reaction. That S is very important, okay? It's showing that something happened. We had a precipitate form. So solid, we mix these 2 solutions, the iron chloride solution, the ammonium sulfide solution, mix it together, and iron sulfide falls out of solution, okay? So we don't break that one apart because it's solid. So we keep that one solid. Everybody okay with that? Okay, you see it in the back? All right, then we have 6 ammoniums and 6 chlorides. So we got our 6 ammoniums, 6 chlorides. So this one is broken into its pieces. Okay, now looking at this reaction, is there anything on the left that has not changed when it went to the right? 6 chlorides? Yeah, so this is 6 chlorides. It's 6 chloride aqueous on the left, 6 chloride aqueous on the right. It's as if the chloride is just a spectator. That's why we call it a spectator ion. If it's the same on the left side of the arrow as it is on the right side of the arrow, it's not participating. So to make the net ionic equation, we cancel the spectator ions. We get rid of the chloride. Because we just want to know what's actually reacting to make that precipitate. What about the ammonium? Same thing, right? So we're looking at the ammonium. Got 6 ammonium ions over there and 6 on this side. Okay, and so then whatever's left is the stuff that's actually reacting. So the net ionic equation is the spectator ions are aqueous on both sides of the arrow, cancel them out. And so here's the net ionic equation, and I still have that 3 plus problem here. So it should be 3 plus, iron 3 plus. So if we could get iron aqueous by bringing it in with the chloride cation or anion, we can get it into solution, and then we could bring in a sulfur with an ammonium counterion and put that in solution, then we could make iron sulfide. Okay. The thing is, let's say we wanted to make iron sulfide, we cannot go to the stock room and find a bottle of iron cations. You can't just find cations on the shelf. They have to be bonded to something. And so you go to find an iron chloride bottle. So you can pull the iron chloride bottle down, and then you go look for sulfide. You can't just buy sulfide. It's not in a bottle, but you can find ammonium sulfide. Okay, so you find a bottle of ammonium sulfide. Then you can dissolve those up into water and then pour the solutions together, and then the iron and the sulfide can find each other and make the iron sulfide. So the only reason we needed the ammonium and the chloride is because they needed to be able to make a soluble form of iron, and they sell it in a bottle, iron chloride. And the only reason we have ammonium in this reaction is because we had that in a bottle, ammonium sulfide. So we really were after the sulfide and we were after the iron. So we go to the stock room. I'm looking for the iron. I was like, I want to find one that's soluble. So iron chloride. Okay, that's soluble. So I grab it. Okay, sulfide. There's a lot of sulfides that are not soluble, like iron sulfide. Okay, so I'm looking along and I was like, oh, ammonium sulfide. That's going to be soluble. So I could grab that. And I know now if I take ammonium sulfide and put it into water, I've got soluble sulfide floating around. And if I take the iron chloride and dissolve that in a bottle, then I've got floating iron around, and I can mix those solutions and precipitate out the iron sulfide if I wanted that. Okay. We do this actually in water treatment, not really with iron, but for some like toxic metals. So if we wanted to get mercury out of our drinking water, okay, so mercury's in our drinking water. Maybe we pull it out of a well or a waste dump or something. We have water that's got mercury in it, higher levels than we want to drink. We could mix in something that has a sulfide and precipitate out mercury sulfide. So we could use this to scrub out these metals, and then we could drink what's left. So this is a way to treat our waste streams. Very effective way too. Okay, so that is the net ionic equation. Notice it's the smallest version of the way things actually are happening. Okay? And it provides freedom for you to pick your reagents. So if I want to make this reaction happen, I need my iron 3 plus. I go to the stock room. I'm looking for iron chloride, but I don't have any. And I'm looking around and I see iron nitrate. That would work too. Okay? So the net ionic equation doesn't tell me what I can pair with iron to get it into solution because it doesn't care. if I could find iron fluoride or iron bromide or iron nitrate, then I can use those too, because that nitrate is going to be a spectator ion. Okay, so we can use this net ionic equation to decide what's important and what's not. Okay. Now, we talked about precipitation. We need to know what's soluble. Like if I was going to the shelf in the stockroom and looking for iron that I could get into solution, which bottle would I pick? I said that it'd be good to pick a chloride, but how do I know that? Or a nitrate. I said, you could pick iron nitrate. How do I know that? So there's solubility rules. So this is another thing that you really need to memorize, because it's not something you can just figure out. It's not like a mathematical equation that you can start with first principles and derive, okay? These are just things that you've got to know. And they're not too hard, but it takes a little bit of effort, okay? So this is saying, in this problem in Alex, complete the table by deciding whether a precipitate forms when aqueous solutions of A and B are mixed. If a precipitate will form, enter its formula in the last column. You cannot do this problem without knowing the solubility rules. And so in the explanation, you'll see the little solubility rules. So here's my version of these solubility rules. So cations, real easy. Here, group 1, alkali metals, all of these guys are soluble no matter what you put them with. Okay. So if it's a potassium, and a sodium or rubidium or cesium, lithium, you're going to know that those are soluble. And also ammonium. So the NH4 plus, it behaves like an alkali metal. It's not a metal, but it behaves like that. So it's going to be soluble. So we wanted that soluble sulfide in the last problem. That's why it was paired with ammonium. Because if you pair it with ammonium, then when you put it in solution, the ammonium comes off and you've got soluble sulfide. So those are the cations. Okay. Here are the anions. So group 7A, the halides. So fluoride, chloride, bromide, iodide. We don't really deal with astatine because it's radioactive, and I've never seen it in any chemical reaction. So we just go fluoride through iodine. Those are going to be soluble. There are 3 exceptions that we should know: silver cation, lead 2, and mercury 1. Okay. So what does that mean as an exception? Well, if I were to put a halide in solution and I had lead 2 plus cations in there, it would grab those halides and it would precipitate out. So lead 2 chloride would be solid after it, not aqueous. Okay, nitrates and acetates are soluble, no exceptions. So if I want to find iron and I want to get iron in solution, I go to the stockroom, I look on the iron section, and I see iron chloride, soluble, iron fluoride, soluble, because those are halides. I see iron nitrate, also soluble. Iron acetate, absolutely soluble. Okay, so if it's an acetate, if it's a nitrate, you bet those are going to go into solution. Sulfates are soluble, but there's a few exceptions. Okay, barium, lead 2, mercury 1, calcium, and silver. And then the last one's the sulfides, oxides, hydroxides, carbonates, and phosphates. They're only soluble with the alkali metals. And so if you have iron phosphate, it's going to crash out. It's going to be precipitate. Iron hydroxide, aluminum hydroxide, all of those, if it's not an alkali metal, you can assume that it's going to be solid and not dissolve in water. It's not going to be aqueous. Now I've got a little puzzle for you guys. Okay, I got this right here. This is a message. This is going to be really hard to understand the solubility rules if you haven't memorized what your phosphate is, or what an alkali metal is, or what about a hydroxide. You know, if you use the word hydroxide and you don't know it's OH minus, then you're going to have a real hard time. So I've got a message for you here. This is in a foreign language, and you can't understand it, okay? So if you haven't memorized your cations and your anions, this is a foreign language. And when you look at a test problem and you're like, I don't even know where to begin is because you haven't learned the vocabulary, right? So if you see phosphate or hydroxide or chromate or whatever, if you would memorize the vocabulary, then you have at least a way to do the problem. If you don't know what a chromate is, then it's just as understandable as this. Okay, so this is a nice little Easter egg. You guys can try to figure out how to translate that, and you'll get my message. So, what's that? No, that's too simple. It's good. All right, so let's do some of these problems. So complete this table by deciding whether precipitate forms. So we've got zinc sulfate and potassium hydroxide. So solution A and B. We have two beakers, one with solution A and B. We mix those into another beaker, and it's a double replacement, right? They switch dance partners and see if the resulting thing is soluble. So what do we have? We have zinc. It's bonded with sulfate, and it's going to now check out hydroxide. And sulfate and potassium are going to interact. And then we will see. So looking at those solubility rules on the previous page, does a precipitate form when we mix A and B? If you see the potassium, look at potassium. Where is it on the periodic table? Group 1, it's an alkali metal, so it is not going to precipitate with sulfate. Plus the sulfate salts are soluble, but zinc hydroxide, it said hydroxides were insoluble except for alkali metals. Zinc is not an alkali metal. So we would say, yes, a precipitate should form. Okay? And it should be zinc hydroxide. Okay. Now, how did I know that it was going to be OH2?
Hydroxide. Oh.
Yeah, the hydroxide's -1. I've memorized my cation. The zinc is a 2+. Okay, if I don't know that, then I got to kind of go from this here, zinc sulfate. There's no Roman numeral there, but I know my sulfate because I memorized my anions. F sulfate is 2-. So I know the zinc is 2+. So I know there needs to be 2 OHs on it. Okay, so once again, an example of you've got to know the vocabulary, you can't learn the language. Okay, what about this one? I said yes. Oops. Okay, so we've got here ammonium sulfide and zinc chloride. So we just swap the two. So ammonium and chloride, those are going to be soluble because chloride's a group 7 and ammonium behaves like an alkali metal. So both of those are soluble in all cases. But here we end up with zinc sulfide. The sulfides are insoluble except when they are paired with the alkali metals. So absolutely we have a precipitate, and this is going to be ZNS. It's not a 2, so that's actually a mistake. So scratch out that 2. Okay. Must be a copy-paste error. Zinc 2+, S2-. Okay. Okay, and then down here we get to zinc bromide or iron bromide and nickel acetate. So then we would look at iron acetate. Well, it said acetate salts are soluble, so that's not going to precipitate. And then bromide and nickel. Bromide is a halogen. Halogens are soluble, so that's not going to form a precipitate either. So acetates and bromides are soluble, so no reaction. They're all spectator ions. So if we wrote this reaction out, the total ionic equation, we'd have iron 2 cations, bromide ions, nickel cations, acetate ions. We'd have the arrow, and those would all be aqueous. And then on the product side, they'd still be aqueous. And so we would be circling all of those as spectator ions. We'd cancel all of them, and we would just have an arrow left. So we just have salty water, nothing, no precipitate formed. So we would say no reaction. Yeah, we got them, they were dissolved, we mixed A and B, now they're in a beaker, and we don't see anything happen because nothing happened. We just have salt water. So we mixed one type of salt water with another type of salt water and made a third type of salt water, but there's no reaction. No precipitate form, no gas was generated, nothing happened. Okay. So next we're going to get into acids. So we need to narrow down our definition of an acid. So there's an ancient definition that we would say that acids produce H+ ions in solution. So hydrogen anion or hydrogen ions, which are H plus ions in solution. And so that still works. It's a good definition, but it doesn't apply to everything. Okay. So HCl gives H plus aqueous and Cl minus. Okay. It's not exactly accurate because we don't have the hydrogen cations floating around by themselves. They actually stick to water and they make hydronium ion. So a more modern definition is acids are proton donors and they donate a proton to water. And so then water becomes H3O plus. So this is a new cation. I've mentioned it before when we were learning our cations, but this one just reinforced it again. This is the hydronium ion, H3O plus. And so this is what's really happening. We put HCl into solution and it reacts with water and produces hydronium ion, H3O plus, and the chloride ion. So that's what's happening with an acid when it goes into solution. Okay, then what's the definition of a base? The ancient definition was bases produce hydroxide ions. So you could look at a thing like sodium hydroxide, put that in water, it's going to produce sodium cations and hydroxide anions. So it's very easy to look at sodium hydroxide, and you see this molecular formula with ionic substances, and you see that, and you're like, that's a base. Very clearly, that's a base. I see OH in the formula. When it dissolves, I'm going to get OH in solution, so that's a base. Okay, but a more modern definition are bases are proton acceptors that produce hydroxide ions. So this is a different kind of reaction. We've talked about the ammonium ion. Where does it come from? It comes from ammonia in water. So if we put ammonia in water, it'll steal a proton from water and leave behind a hydroxide. So this means that ammonia is a base. It's producing hydroxide ion, but it's doing that because it's accepting a proton. So when we get later on, we start talking about the electrons around nitrogen, we'll see that there's a lone pair here. And we have an H plus come over here and get close to that lone pair. And when the H plus leaves, it leaves behind its electron, and we end up with OH minus. Okay. So that's what's happening. We're forming ammonium cation and hydroxide anion. So when you have a household bottle of ammonia, okay, it also could be described as ammonium hydroxide. Okay, so it's ammonia dissolved in water, but when it goes into water, it makes ammonium ion and hydroxide ion. So it's a very basic solution. Bases attack things like fats and oils and greases. Okay, so whenever you're trying to clean up things in the kitchen or bathroom and so on that are oily or greasy, then ammonia is a very good cleaner because it attacks those greases and oils. It actually attacks the double bonds and makes them into organic acids, and those things are more water soluble. So it attacks the grease, makes it into a water soluble material. It's called the process of saponification. That word soap is in there. So you could take ammonia solution, mix it in with fat, and make soap through the process of saponification. And that's the ancient way of making lye soap. They would take lye, sodium hydroxide, boil it with fat, and it would make soap out of it. Yes? Oh, yeah. There's like beef tallow and so on. It's like coming back now. Yeah. So it's really good for your skin. Now, the base is not good for your skin because what do you have in your skin? Fats, lipids, right? And so if you get base on your skin, it feels real soapy. It's because it's making soap out of the fat in your skin, right? And so you wash it off, you're washing the base off, you're washing that soap that you just made off. Well, it's drying out your skin. So it's very important if you're going to use a ammonia cleaner that you use gloves because that will attack your skin and also concrete. If you're ever making up satcrete or concrete, it's a
That'll
very,
burn you.
very, very basic substance. And the burn is actually so drying your skin, it starts to crack. So it feels like a burn, but it's really saponifying the fats out of your skin. I didn't follow the directions, and I was just putting in a basketball goal and cementing it in. And I was just sort of doing the final touches with my hands without gloves, patting it down. And I thought it's a few minutes, right, without gloves. And I washed it off. My skin got so dry and so tight and so it shrunk. I couldn't straighten my hands out for a day until I generated enough moisturizer to get the skin flexible again. I figure if I had forced my hands to straighten out, my skin would have cracked and it would have been really painful. So I was walking around and my skin looked ancient because all of the good fatty stuff in the skin had been sucked out. Yes.
Specific one where it hits your skin and it kind of evaporates. It looks like it evaporates as soon as it hits it, but it starts eating at your bone. And the only way you can stop it from getting to your bone is to rub it. But even if you rub it, you get cancer.
Oh my gosh.
Which one's that?
I don't know. I've never heard that. I've never heard that. I hope we don't have any in the building. But hydrogen fluoride gas is one really dangerous substance because if you get exposed to hydrogen fluoride gas, it will eat through to the bone. You can't really wash it off. So that's one of the most dangerous substances that we know of.
The professor said the cancer was the best case scenario.
Yeah, so I don't have any idea about that. That sounds terrifying. Yeah, but basic solutions are more dangerous than acids, in my experience. It's for your skin because we're surrounded by a little protective coating of dead skin cells, which is protein. And base hydrolysis will break down proteins, but acid won't attack proteins as well as base. Okay. Now, it's very important when you're doing titrations in the lab to not fill the sodium hydroxide solution in the burette above your face because it can splash and it can maybe get in your eye. And again, your eye is cells, proteins, and so on, and it's very dangerous to your eyes. So sodium hydroxide solution, that's probably one of the more dangerous labs that you do is titration. So you always take the burette out of the holder and fill it down here so that you don't get anything splashed in your eye. Your eyes are very sensitive. That's why we want the full goggles, because you may be a really good chemist, but your neighbor. That's the real reason why you wear those side goggles, because you don't know who's next to you, and you don't know how sensitive or how careful they are. Okay, so let's recognize acids and bases and other properties. So here we have, of course, ionic substances are ionic and they'll break into solution. But then the acids we will classify as molecular. And so if we go down this, we see a magnesium nitrate. That's going to be an ionic substance, no problem. Nitrate is not an acid. It's just nitrate is an anion, and magnesium is not an acid or a base. Okay. Sodium chloride, again, chloride, sodium, neither one of those are acid or base. But here we get to HCl. So HCl is an anion plus a cation. It's going to be a molecular species, and it's going to be an acid. And then hydrogen or sulfuric acid, H2SO4. Again, we made that, taking the sulfate anion, 2- and adding 2 protons to it to make a neutral H2SO4. We would classify that as a molecular substance, and it would be an acid. So just going down through, and again, these are really fast. So I think even if you haven't started the homework till today, you'll be able to hammer through this now that we've talked about what an acid and a base are, and you've seen some examples. Okay, but for bases, we're looking for that OH. So, or ammonia. Ammonia would be that one exception. Okay. So let's talk about neutralization reactions. Okay, so let's, what's going to happen with this? We're predict the products of this reaction. That is, complete the right-hand side of the chemical equation and make sure your equation is balanced. So we're looking at this equation. What do you see when you look at that equation? What's the HNO3? Nitric acid. So it's an acid. What do you see with the barium hydroxide? Hydroxide. You see a base. Okay. And so this is a neutralization. An acid plus a base makes water. So let's write the full ionic equation. So over on the left side, we have, that's crazy. Why? Okay, so I've had to balance it. We've got the 2 hydroxides. And so when we balance it, we're going to end up with 2 nitric acids. Okay. But anyway, we end up with 2 hydroxides that come out that are aqueous. We have the barium 2+ that's aqueous. We have the nitrate aqueous and the proton that comes off aqueous. And then the proton and the hydroxide get together to form water. And so then we still have the 2 nitrates and we still have the 2 barium ions. So let's write out the molecular equation. So since we had 2 hydroxides, we need 2 protons. And so that's what's going to require this 2 protons and the 2 nitrates. We're going to form 2 water molecules and the barium nitrate. And just for grins, let's write out the net ionic equation. So if we go up here and we cancel the spectator ions, barium was a spectator ion, the nitrates were spectator ions. So they didn't participate in this neutralization reaction at all. So we have 2 cations plus 2 hydroxide ions making 2 water molecules. So that's the net ionic equation. And you could even simplify that by dividing all 3 of those by 2, but just not doing that, just keeping everything the way we had it up above. It's the cation plus the anion equals a neutral water. So this is an acid-base reaction, and that's why we call it neutralization. That you probably didn't really think about that word much, but we're making something neutral, meaning not charged. Right? Cations are positively charged. Anions are negatively charged. But something that's not charged is neutral. Kind of like a neutron. It's not charged. Okay? And so here we have a cation and an anion and a neutral species. So that's what we mean by neutralization. We're taking the hydroxides and neutralizing them with acid, or we're taking an acid and neutralizing it with hydroxide. And that's what you do if you have an acid spill. You take sodium bicarbonate and you neutralize the acid, and it fizzes and foams and makes CO2, but you're neutralizing that acid and making it not hazardous, okay, so that it can be easily cleaned up. Now, why Alex doesn't use liquid or aqueous, I don't know. I wish it would, because I think it makes the problem easier. When you're looking at this equation, you see over here liquid water, right? And it comes from aqueous acid and aqueous base. So aqueous base, aqueous acid get together and make neutral water that's liquid. Okay. So I think it's, I'm going to put in a suggestion. Guys, use the state of matter like aqueous, liquid, solid. It's important. Okay. Now let's recognize reactions. We're kind of got to speed up a little bit. So identifying precipitation, combustion, and acid-base reactions. So we're looking at this. What do we see? Yeah, look at that right there, solid. So when you see that, you know it's a precipitation reaction. It's also double replacement because they switch dance partners. The potassium went with the nitrate, and the bromine went with the silver. Okay, so it's precipitation and double replacement. What about the next one? Yeah, I got fuel and oxygen. So that's definitely a combustion reaction. So combustion. All right. Let's look at another one. I'm forming liquid water, so at least now they're using it. Acid base, right? And let's check it out. Let's see, I've got a proton there. I got a hydroxide there. Okay, so those are making the water. So that's going to be a double replacement because they're swapping partners, and it's going to be acid base.
Is that always going to be the case? It's always going to have double replacement?
Yeah. So here we have a solid So those ought to go fast. So there's hope for getting this one done tonight if you haven't started. Okay, let's do another one. I was trying to look for some of these other ones here. So which one is this? Yeah, so we got A, B, making AB. Yeah, so that's combination. And then the next one, decomposition. Yeah, you're taking a single substance and breaking it into multiple parts. So what about this? Weak and strong acids. Okay. These are your strong acids and strong bases. And we're going to be nice to you in this course. There's only one weak acid. At this point, we want you to learn, and that's acetic acid. So acetic acid is an organic acid, and so it's going to make acetate and H3O+. That's your weak acid, and ammonia is your weak base. So if it doesn't have acetic acid, then it's not a weak acid. It's a strong acid. And if it doesn't have ammonia, then it's going to be a strong base if it produces hydroxide. So ammonia NH3 would be the only one that's a weak base. So here, quickly, we've got ammonia here. The compound is NH3. That's a molecular substance, and that's a weak base. Okay. And here we have sodium nitrate. It's not an acid or a base, right? So here's NaNO3, and that's an ionic substance. So you have a cation and an anion. It's going to dissolve in water. No pH change. We don't know what pH is, but no change in acid or base. Here we have acetic acid. So it's written a strange way, but this is the way. You got the H here for the acid part. This is the acetate anion, molecular substance, and it's going to be a weak acid. So all the other acids that you're going to come across are going to be strong acids. Here, KCl, it's just potassium chloride, ionic substance, not an acid or a base. Perchloric acid, molecular substance, and strong acid. Yeah. And then acetic acid, once again, molecular and weak acid. So these ought to be pretty quick and easy to get into pictures. And so we're good. 2 minutes left. Y'all can go. If you have a question, come on up.
Those are the so of course those are super weak because like I have